lecture today we're talking about the use of ODE in Panda and one of the applications, which was for the golfing game in Toontown. I'd like to start this by saying that this physics lecture, had to move over for the camera, is not going to contain a lot of math. I'm not a very good math person. I've done a few things with math, but mostly this will be a practical discussion of using physics in video games, the different types of physics systems that are out there, what to look for in a physics system given your application, things like that. My background as far as physics programming goes is I've actually programmed some 2D physics, collision detection, things like that, with floating bodies that aren't connected via joints or anything like that. So I've got some working practical knowledge of doing simple physics from scratch, but I've used other systems for more, what's the word I'm looking for, more impressive results. So let's talk about the two physics engines that I've used here at work are typically the Panda physics engine and ODE. And the difference between the two, and the reason that we had to use ODE for golf, if anybody is curious in that, maybe I should give some background about the golf game. There's not a whole lot, but we decided we wanted to do golf for Toontown, so we started exploring different physics engines. Started with the Panda engine to see how well we could do golf. Well, there are three components in a physics engine, at least by my estimation. There's collision detection, which is spheres and boxes, raycasts intersecting each other, and that can be very complicated. And that's, it's very useful to have. Then there's also motion, which is, saying here's the momentum of an object, it carries over this motion. I'm going to add force, things like that. And then there's the reaction phase, where you take and you put those two things together, which is to say the collision between two objects at this point creates this force that gets imparted on both of them. And the Panda physics engine wasn't really set up for doing the reactive physics. It's sort of set up for doing game logic physics. Things like I move into this sphere here, and this activates this door to open, or it has a pusher model is about as fancy as I really found working well, which is to say I'm going to keep you out of walls. And sometimes you don't want the more fancy reactive forces going in an engine. Like ODE, trying to put ODE just for running all of Toontown would be a bad idea. I mean, you get all these sort of unknown forces pushing you around, get reactions bouncing, things that happen when you don't want them to happen. So for the physics engine, it's very much looking for features that you don't want as well as looking for features that you do want. Physics is, particularly in game engines, it's a big compromise, and you cannot simulate these things 100% correctly. And what that means is that the laws of conservation of energy just go out the window right away. There's going to be more energy or less energy in a given system, and if the system tends to build up energy, it sort of hits a critical mass, not unlike a nuclear explosion, and everything flies apart at the speed of light. So you need systems so if you have too much complexity in the system, that tends to happen. You want a system that you can keep a handle on. You don't want unknown results. And that's the reason why Panda is really good for some things, ODE is really good for other things, and why we haven't just ripped out the Panda physics for a more fully featured set, which is ODE, but Panda physics is sort of a more stable, more reliable engine. So, what is ODE? ODE stands for Open Dynamics Engine. You can write that down. Thanks. Sorry to single you out, Simic, but it's just another acronym. It's fun. It means a lot of different things. They're on version 0.5, and they claim to be a fully featured physics engine. So I think that's kind of cute. They're not even on version 1 yet, or anywhere close to version 1. But they have people out there using the products. It's rigid body physics. Rigid body, means that there's nothing bendable in it. They're not doing, cloth or anything like that. But there is a lot of other things in this simulation. There's joint simulation, and joints are when two rigid bodies are connected together. So let's go over some of the. Oh, and then the third component in the simulation is collision, which is, again, spheres, boxes, things like that. Let's go over what some of those things have. Rigid bodies, again, are just sort of a mass. They're sort of a point in space that has a mass, or not even a mass, although you can simulate that, but it's got a position, a linear velocity, an orientation, and an angular velocity, and sort of a point for imparting the physical forces onto an object. Then you've got the joint types, and this is actually sort of one of ODE's big things, is that it can simulate lots of multiple joint types. There's the ball and socket joint, which is sort of the how my fists are going together. You've got one moving around in the ball like that, or it's sort of like your shoulder. It does the hinge joints, so it sort of constrains things to open up and close. It's got sliders, which are just things moving along a linear path, and they can have free rotation. But there's lots of different hinges. They've got hinges for almost every application, and so you can look that up. There's 3 or 4 that I haven't mentioned, but they're important. Another interesting thing about the way that they do collision systems, again, is that they don't really, there's 2 ways to do a collision system. There's a way when 2 objects meet, you detect that collision and you can immediately impart forces. And that's sort of an instantaneous physics system. A lot of people, when they do homebrew, they do this sort of thing. It creates problems because if more than one object is involved in a collision, then 2 of them sort of come up, and they come up with a solution to that collision, and then the 3rd object doesn't know what's happening. Is people following this? And then there's a deferred physics simulation, which is you store up all of the collisions that happen or all the contacts that happen in a collision, and then you figure out, you apply all those forces after you've done the entire collision run. And ODE does that by creating joints for collision contact points. So when a sphere intersects a cube, there's not anything extra. There's nothing special about that. It doesn't just instantly apply the forces. What it does is it creates a joint at that point. And that joint actually creates the physical forces that you see, when you see the objects bounce off of each other. So that's how that happens. So, talk a little bit about collision primitives. Just because I want to go over it. There are, how many of you are familiar or have used physics simulations or are comfortable using physics engines? Okay. Well, one of the things that people always ask for is accuracy in their collision detection. They want, working with artists in particular, they want the collision to look exactly like the object. They want every little facet to hit it. And when you're creating collisions, when you're doing collisions against large solid objects, computer games, they happen frame by frame. So if 2 objects happen to pass through each other, either they'll pass through each other or you have to do something clever to stop that. And you can do something clever to stop it, but that usually just sucks up your frame rate. So the better thing to do is to make it simple, make it fast, understand what it's going to do, and sort of design your gameplay around that. Well, there are 2 types of collision surfaces in the world. There's solid collisions, which are boxes, spheres, ground dimensions, or whatever you want to call them. And then there's infinitely shallow collision detection zones, which are what you get when you start using polygonal models. Polygonal models for collision detection. So if somebody wants to use a character mesh for collision detection, that's well and good. But if you shoot a small enough object through it, the mesh infinitely thin, connected points and vertices. You've got your box. Here's frame 1, frame 2. It's over here. Whereas if you have 2 boxes intersecting each other, a box is solid. The computer realizes what that is. Here's frame 1, frame 2, it's inside. You catch a lot more collisions. Things don't sort of fly through them. So, as a caveat, it's always preferred to use solid collision surfaces when you can. A good example of this is And a feature that they're adding in ODE, which we used for the golf game, is we needed a ground. And ground doesn't really look like a box. It doesn't really look like a sphere. It looks like a two-dimensional functional plane. There's no overlapping points, but it covers the surface. So you've got this sort of connection of interlocking points that's down. You've got your golf ball up here, and gravity always wants to be pulling the golf ball through this. And if all things contribute together and they get through that infinitely small plane, then you've lost your golf ball. One of the new features that they're adding to ODE is what's known as a height field, which is since you know that the ground above, or that the sky above it is empty and the ground below it is solid, people are working on making actual solid ground where you know that if it's below the plane, you should shoot whatever's below it up. So that's kind of interesting. And there's a plane structure which is sort of like that, only it only has, a plane is flat. So oftentimes you'll use that for simple games because it's solid, but you can't have the interesting terrain features from the plane. So that's sort of an overview of ODE collision surfaces. Now, talk a little bit about how to set up objects in ODE, and this is about as detailed into actually talking about the physics simulation as I want to get, because I'd like to keep this lecture somewhat light and not get too bogged down with details. But ODE has two sort of separate spaces going on. They've got the world space, which is all of your rigid bodies, or all of your bodies, that being all of your masses and things that have velocities and angles and angular velocities and joints and things like that. And then they've got the notion of space, and space is considered your collision geometry. So you've got these two worlds going on at the same time, and they sort of have to link up to one another. So when you first create a world, or you're trying to set up your ODE physics simulation, the first thing that you do is that you create the dynamics world, which is the place where you've got all your masses, where all your forces get implied and things like that. The second thing is your collision space, which is what I just said. It's all the collision detection. But after you do that, you've got to link all the bodies to all the collision surfaces, all the collision geometry. So there's a step where you've got to link those two things together because they are separate ideas, they're separate notions. And then when you run the main loop of this, so you're trying to run a single simulation step. And there's different ways to order all these things, and they have different effects, but the suggested way of doing it is to apply forces to bodies. So if there's any new forces, if there's anything that you want to control, you say there's a rocket on your car or something like that, you apply the new force onto the body. The second step is you call the collision detection. And the collision detection sees if anything's intersecting, and then it can, if they're overlapping, it creates a joint there. Like I said, the collision detections are all handled by joints. The third step is actually running the simulation. So you take the forces, you take the joints, and you see what would happen. In this case, the ball, decides to bounce off the box because the joint's telling it to move out. The joints are sort of black magic. I don't know exactly how the collision joints are set up or how they're determined to move them around. It's sort of the engine sort of handles it, in a black box way. So, and again, I said that there wasn't going to be a whole lot of math in this. Some interesting things, like I said before, physics simulations in general aren't perfect, and in order to avoid having them blow up like some sort of nuclear reaction, you have to be able to bleed energy out of them. And ODE has two methods for doing this, for which I'll just go over very briefly. The first thing that they have, and if you get involved in it, you're going to see this and it's going to confuse you, is called ERP, which stands for Error Reduction Parameter. And all this really means is how inaccurate are the joints allowed to become during the simulation. An ERP of 0 means that the joints are basically meaningless. you know, you've got your ball joint, but the two sides can float off, and there's nothing going to be pushing them back together. In the ERP of 1, means that those joints are never allowed to leave each other. They're, you know, they're going to stay hard and fast no matter what happens. But what happens with this is, you know, there's imprecision. It's a simulation. You can get jitteriness of this because new energy might be created in this sort of thing. It's creating a hard world where random circumstances can happen. So what they typically do is they default this to a value of 0.2. That's sort of meaningless standing here in this lecture talking about it without you being able to, you know, get it ODE and try it out. But what it's saying is that they feel it's far more important to bleed out the energy than it is for those joints to be rigidly attached, because they will catch up. They've got another thing that's very similar called CFM, but it's just sort of the same idea. It's sort of saying how soft do I want these collisions to be, how far do I want to allow them to interpenetrate before they go on. I don't want to get too much, I'm not going to go much more into that, but I wanted to talk about that just so you guys know that they're there. Now for any, oh, did you have a question? Okay, never mind. Now for any physics simulation, another big feature is the collision bit mask. Do people here know what collision bit masks are? Do I need to go over that at all? Basically what they are is they're a way of categorizing objects into what can collide with what. And so they're really just a big string of, you've got object 1 and object 2, and you've got this big string. We'll just use 4 bits for this. You've got 0, 0, 0, 1, and you've got, say, 0, 0, 1, 1, and we'll throw out object 3, which is 0, 0, 1, 0, and yeah, sure, binary is fine. But all this means is that when object 1 collides with object 2, or when it's considered for colliding with object 2, because they overlap, you know, they're allowed to collide. Similarly, when object 3 hits object 2, those overlap, so they're allowed to collide. But if object 1 were to collide with object 3, there's no overlap, so the collision is ignored, and they pass through each other. And this can be used for game purposes, saying that, you know, bullets can collide with your enemies, but not with your friends, that sort of thing. There's a little bit of difference between Panda and ODE in that, I'm not sure on this one. ODE has what's known as category and collide bits. So there are 2 separate bit masks for that. They're saying, okay, what can collide with me, and what can I collide with? And it's just sort of a nice way to break those up. It's a little bit easier to keep track of, but you can get by with only 1 bit mask if you really want to. It's a little bit more painful though. So. All right, let's talk a little bit about using ODE and Panda again, or in theme parks. Again, I said the application that I used it for was golf. ODE is not as integrated into Panda physics as its own physics, obviously. It's sort of a separate module. So if you actually want to use ODE, it's not going to be part of the scene graph. It's going to be off in its own world and space, and so you need some way of moving that over to Panda. And the way that we did this, because we were only simulating 3 or 4 objects at a time, was we just had a thing at the end of the loop that says, I've got equivalent objects in the space. I'm just going to move all of my Panda scene graph objects to match the ODE world and space objects. So it's not terribly efficient, and it would be a horrible thing if you were simulating 10,000 objects, but if you're only simulating 2 or 3, it works out pretty well. Otherwise, you'd want to run, you'd want to do something in either in C++ to do the same thing, or you'd want to have more tight integration to where the scene graph and the spaces and worlds actually had some sort of matching up. But that's how we did it, and it worked out pretty well. Another big fun difference between Panda and ODE is ODE uses a fixed time step. This is an interesting thing. Most physics engines, or at least a lot of the physics packages that you'll get out there, use a fixed time step. And this basically says that when I'm simulating, between each step, it's going to be a 30th of a second or something. Some things, like I don't know, but I don't think Panda uses any sort of fixed time step because it's not doing reactive physics. It doesn't really matter as much. But in the case where your frame goes, say, a 15th of a second, in order to deal with a 30th of a second time step, you actually have to run 2 physics frames for each visual frame you do. So there can be some, if they would get too far out of whack, it can be sort of hard to catch up. But usually ODE runs really fast. When we were doing it for golf, it ran like 900 frames a second. So something to look out for, though. And if you do get behind, odd things are going to happen. Let's talk about physics restitution. And this sort of goes back into the idea of when those 2 objects were colliding with each other. Not only do you have to impart a force back, but most things actually move this object physically out of that other object. And those 2 things are sort of connected. ODE actually combines the restitution with the force, moving the object out, or at least it likes them to be consistent. A lot of homebrew physics simulations will look and say, how far am I into that object? And based on how far I'm into that object, that's how much force how much force I collided with it. That's generally a bad thing to do because you don't know, the frames don't always match up, but a lot of people do it. You get a lot of jitteriness and imprecision out of it. So I would suggest not doing that if you're making your own physics system or looking for a physics system. But ODE does it, at least to a little extent. And one of the downsides from that is that you have to have consistent time steps. So let's see, we covered that. Now let's talk about, and one final thing before I move on to the application-specific area of using it for golfing is collisions. One thing that happens when you collide with something else, invariably you want different reactions to happen when different things collide. You want, okay, if a dirt object collides with a stone object, it's going to go splat. If 2 stone objects collide with each other, they're gonna bounce off of each other. So you want to be able to determine what sort of material hits happen. The tricky bit about this is that you're going to sit down and you're going to say to yourself, okay, I want to define a material. I want to say it's this soft, or I want to say it's this bouncy. ODE doesn't really let you do that. And it's not really a bad thing. What it really does is it says the collision between 2 objects, or between 2 materials, is soft or bouncy. And we set this up. We had to make our own matrix of collision types and put this in our ODE implementation, but it's fairly standard. I've seen other people do it. So you really have to go through and say, for each type, you have to say, what's the collision going to be like? And it can be a lot of work at first because it goes up, it's a square type thing. So if you have 5 different materials, you're doing 25 entries, and if you have 100 different materials, you're doing 10,000 entries. But for practical purposes, most games end up using, mini games or even large games end up using, like 4 to 10 materials. So it's not that big of a deal. All right. Talked about most of that. All right, going on to the golf game. So the golf game in Toontown is a lot of fun. It's a 4-player distributed game where each person takes a turn hitting a miniature golf ball. It flies up, and they're trying to get into a golf cup, just like any sort of golf game. We had several challenges in this. The first thing that the first big problem with using a real physics simulation in this is that they're not consistent at all. You can have the same objects with the same inputs across different computers and impart the same forces, and it'll come up with different answers. ODE is not consistent. You could probably write a physics engine that's consistent, but it is probably going to end up being really slow. So the first problem we had was the golf ball would sometimes go in the cup on some people's machines and not into the cup on other people's machines, and this didn't really make a good game. So we had to come up with a way to make it consistent. Well, there are 2 ways to do this. You could either check the consistency as the object moves through the air and try to correct it, having a server and all this other stuff. And we didn't really care about that because there's not really much interaction with the golf ball after that initial hit. you're just really implying one force. So what we ended up doing was having whoever hit the golf ball generates a movie of that golf ball going through the air. ODE runs at 900 frames a second. Toontown displays this at like 30 frames a second. So if you do the math, it ended up taking about a tenth of a second to generate all the frames. From there, we did a compression algorithm on it to knock it down to like 50 or so keyframes, and then we just sent that out to all the client computers. At first, we had the consideration of, okay, what machine do we want to generate this on? Because we were a little bit worried about cheaters, and we were also worried about using up server CPU time. So the first inclination, if you do it on each individual client, somebody could hack the client and just instantly put the ball in the cup, and that wouldn't be good. If we run it on the server, the problem is that each one of these little strokes takes a tenth of a second. And while that's not much for an individual's machine, if you have 100 people or 1,000 people playing at once, you can quickly, destroy the server with all these tenth of a second pauses. So what we ended up doing was randomly assigning individuals in the game to generate the movie and then send it out to everyone else. So a cheater could still cheat if they're in a 4-person game, but they can only cheat 1 out of 4 times randomly. And it's going to confuse the heck out of them that why did their cheat work this time and why didn't it work. And if you try to cheat and the computer knows that it wasn't your turn to report, it'll pop up a suspicious flag, and it'll say that, okay, this person's probably hacking, and it'll show up in the logs. So that's how we solved that problem in our golf game. Oh, another solution that we had come up with, although this would have been hard, is we were talking about making a separate golf Uber dog. If anybody knows the concept of Uber dogs, we basically have a separate computer system devoted solely to generating the golf physics, and then the server can call that up, or the client can call that up. And if that bogs down, it doesn't bog down everything else. But setting up an extra Uber dog machine requires extra hardware. We have to call all these people, and it'd be sort of a pain in the butt. So we decided not to do that. That's about it as far as I have for talking about ODE. I said this would be a short lecture. It took about 25 minutes. Does anybody have any questions? Red's going to have
stuff to add.
Red's going to add something. Do you have a quick question?
I do have questions.
Okay.
When you're representing all this stuff, do you use vectors and mass, or how do you dictate different stuff when you're representing each different object? Do you have to tell the API, how much this weighs and how fast it's moving?
Yes, you can actually attach. You attach masses to the rigid bodies.
Okay.
So the rigid body, the thing that has the orientation, that has the position, the angular velocity, you attach a mass to it, and from that it can sort of figure out how much energy it went into it. Oh, that's another good thing to bring up, and another reason why you would want to use Panda physics as opposed to ODE physics for certain things. ODE likes to be a natural sort of simulation, sort of flowing. It likes it if you don't move things around willy-nilly. Because in order to move an object from here to there, you sort of have to impart an infinite amount of force to do that. Or if you want an object not to move, there are a few ways to do it. One, have infinite mass or things like that. And that's bad in ODE. There's another way to do it. But yeah, it doesn't like moving objects around, especially if they're attached to joints. If they're floating objects, you have a little bit more room to do that. So I don't know if that answers your question. Your original question was just about what's attached to it. Anyway, Red has another use example, and I'll let him do that. It's for a mini game that he created recently where he used ODE.
Okay. First, some tips. The default ODE system is meter kilograms second. So if you're using it with a default Panda system, like which uses feet, change your gravity to 32 feet per second. Also, it has a random number generator. So if you want to, there's no guarantee it's going to be consistent across clients, but if you want to try at least make it more consistent, you can set the seed of that random number generator.
Why does it use a random number generator?
It was used for, as I understood the documentation, on the order in which the contact joints were created for the collisions. That's what the documentation said. Anyway, so imagine that this is an ice rink and the toons are sitting on tires. And as players, the toons can choose which direction they're gonna go off and how much force they're going to apply to themselves. So they're all gonna choose different directions and different forces. And then again, they're all gonna say, yes, that's what I want to do. And then what the game does is, for each client, it sets and gives them all the same inputs. Like for each of these tires, which direction and how much force they're going to be going. And then for each client, it does it all at the same time. I forgot to add, the goal of the game is to be as close to the center as possible. So they're all going to be bouncing around each other and trying to get as close to the center and pushing each other away. The difference that in the golf game was only one client was simulating the physics. Here we have all clients simulating the physics. I could get away with it because at the end of the simulation, each client would report the positions of all 4 tires to the server, and the server can arbitrate and detect if somebody is cheating. Like, hey, you know what? Client 4 is always in the center. Well, for the other clients, his tires are like over here or off. So I could do that. Also, I found that there is some stuff you can do in ODE to try to make it more consistent, not necessarily across clients, like making that random number generator, setting the seed. I found that, for example, client 1 would run this simulation with 1,500 steps. Client 2 would run it like maybe 1,503. So in terms of gameplay, where the final tires end up, it's very, very, very close. So for this particular case, it was close enough. And then the server would arbitrate and figure out the final resting position of the tires and send it out across to the clients all over again. And this is where you really end up. So that's about it. That was just another example of how you can use ODE, a different way of doing it. And it all depends on how you use it, and I guess for the game type that you're doing it. That's fine. Any questions, by the way? Okay.
I have
okay.
a question. From what I've seen, both instances of ODE have been used in 2-dimensional space?
Well, in golf, it can shoot up into the air and it bounces off and things like that. The golf is a 3-dimensional game.
Oh, is it?
Yeah.
Oh, okay.
Yeah. Well, did you have a question?
There's nothing limiting it to 2-dimensional space.
Oh, okay.
You could create a 3-dimensional cannonball game with it.
ODE actually wants to be 3-dimensional. You have to do sort of, and in simple 2-dimensional cases it works pretty well, but there's some cases where it's hard to keep it 2-dimensional, and then you have to do some fancy bits to keep it being 2-dimensional.
Right.
So, but ODE wants to be 3-dimensional, if that's what your question was.
Cool.
Are there any other questions?
Why not run the simulation from the server and interpolate the position on the clients?
It takes too long. Yeah. And
you get lag time off the server. And actually, I was thinking about talking about how to actually run. If you're interested, I can talk about how to run a server talking to clients in efficient ways to keep those synced up between the clients. I have done one game that's not related to ODE that sort of does that. I can give some tips on that, but are you interested in that?
Yeah.
All right. So, something very similar, but a game that I programmed, when I was talking about the 2D game that I programmed, is this little car combat arena game I have, where I've got these little cars, and they go around and they shoot at each other and they move forward. And each different client controls a different car. And this is more set up like your typical deathmatch game, things like that. And in this case, the first thing you want to figure out, there's a couple different things to consider, is who owns each object, right? If you want somebody to feel like they're really controlling their avatar in the game, you want to sort of trust them positionally. And this works very well for action games, not so well for MMOs or where you're really worried about people cheating. You can sort of choose to have the server take the controls from the player and update the positions, or you can have the players control their own positions, which typically works a little bit better. But you get this problem in that you've got these different objects, and each one is being controlled by a different entity. Some are controlled on the server, some are controlled on this client, some are controlled on this client. And how do you make them look smooth? How do you not make them just sort of jump around? And this is a problem that I had to deal with. And what you end up with is a case where everybody's got their own visualized positions of these objects in the game. So I'm running the simulation on all objects in the game, and so are you. So we're each controlling them, but there's one final definite correct one. And so if I'm controlling this car, I think it's right there because that's the center of the object. If I'm looking at this and this is you, on your machine, the car is over here. So what I do is you send me the data that says you think the car is over there. I put a spring that's attached between the two, and I sort of suck the car into the location that's the authority position. And that sort of lets it happen gently. And the spring gets more force the farther the two are away from each other. And it creates a nice smooth effect, and things don't have to jump around because of that. A problem that you get with that you want to be careful on is if you've got a large blocking object, you can sometimes get in the case where the authority object is on this side and your local version is on this side, and it's sort of trying to pull the two through each other. So you just have to be able to detect that and allow the authority object to pull the local version through the object. And then it's as important as possible to keep the simulations, the physics simulations between the two clients, or between the different clients as close as possible. So you want to send input information, like you want to say, here's the controls that I'm holding down from this client to that client. Because the more information that you have on each individual client moving that, and the more true physics simulation, the more they tend to get matched up. And it's good for games where you've got physics that where you can't stop suddenly. There's a lot of momentum in cars. There's a lot of momentum, like in ship combat for pirates. So if the physics can be very predictable, this works really well. Now, well, if you've got something that's sort of like atomic physics, like golf balls that are flying around in all sorts of random directions, this sort of breaks down and it's not so easy to do. So, is that helpful? Okay. Any other questions before we wrap up? It can be about anything. Well, ODE related. All right, I guess that's it. So.